Alright, so today we expand on the previous section, continue with the polar theme. Real quickly, last time we introduced the polar coordinates, we explained how it was reflected, or how it compares to the Cartesian. We explained the famous method of graphing, plotting points. We talked about some of the most famous graphs. The roses are also super famous. Talked about different techniques for graphing, plotting points, recognizing famous ones, or analyzing this stuff about the maximum R and the minimum R values and where they occur to plot down the petals. Today we want to expand on that. Another famous topic and perhaps another technique for graphing is to convert these polar equations into something that you already know. To convert them into Cartesian. So this section is, roughly speaking, the theme for the section is converting equations, not just from polar to Cartesian, but backwards. And the best way to do it is probably just start off with a couple examples. The idea here is to recall we had this very famous conversion, the dictionary, right? This dictionary converts. If you've got r's and thetas, this tells you how to get your x and y's, and vice versa. If you get x's and y's, this tells you how to get your r's and thetas, although the path this way is not unique. But the idea is, roughly speaking, to take equations and make use of these dictionaries, both of them, so that you can convert. For example, if you've got this timeless equation, this is the equation of a circle, and you wanted to convert from Cartesian, obviously this is Cartesian, to polar, you'd want to look at the dictionary and find a ways to exchange that. Exchange an x squared and a y squared. I have to exchange x squared plus y squared for r's and thetas. And this tells you, if you look at it carefully, this tells you exactly the exchange rate. Every time you've got an x squared plus a y squared, you can exchange that for an r squared. So this one could become, if I wanted to convert, this would become r squared is equal to 4. And that becomes two possible options. R is equal to 2 or R is equal to -2. And in fact, both of these would be legitimate equations for the circle with radius 2. That won't work and that won't work. And we see this phenomena that points in the polar plane don't have a unique name. You could have two different equations that look different, but yet if you look at the graphs, the graph of each one, the graphs are indistinguishable. Clear? Let's try it again. Suppose you had something else that's famous. Y is equal to x squared. How would you convert that? Well, if you look at this, you could always exchange a y for an r sine theta. And you can always exchange an x for an r cosine theta. So that would be a plain and simple way to do it. My y, I would exchange it for an r sine theta, and my x, I would exchange it for an r cosine theta. Of course, this quantity is squared, so that would leave me with r sine theta is equal to r squared cosine squared theta. And there you go. This would be the converted version of the equation. This one was in Cartesian, it has x's and y's. This one's in polar, it has no x's and no y's, only r's and thetas. Okay? Actually, converting this one is really easy. Again, you can always exchange the y. You can always exchange the y for an r sine theta, and you can always exchange an x for an r cosine theta. So this is a famous one. This is y equals mx plus b form. A famous one in the Cartesian plane in your algebra class. So we could convert it. This would be, I'm going to convert in white. This would be r sine theta is equal to 3 times r cosine theta plus 5. And that would be converted. This is Cartesian. This would be polar coordinates, only r's and thetas, no x's and y's. Converting this way is really straightforward. Every single y can be exchanged for r sine theta, every single x could be r cosine theta, so the equation could be really complicated. The conversion would be only one or a couple steps at most. Converting the other way is much more interesting sometimes. For example, r equals 5. There is nothing in our dictionary here that tells you exactly how to exchange on r per se, r all by itself in terms of x's and y's. However, there is a way to exchange an r square in terms of x's and y's. So sometimes you have to get a little creative and try to figure out a way to tweak the equation legally so that you can make the right exchanges. I'm going to make use of this. Watch this. This is a famous idea. If r is equal to 5, that would imply for sure that r squared must be equal to 25. You know, assuming we can square both sides. And the advantage there is that I can exchange the r squared. I can exchange the r squared for an x squared plus y squared, and that's equal to 25. And now I've done it. We really did it. Now we have no more r's and no more thetas. We only have x's and y's. This is a famous conversion of the equation. Okay, pretty easy, huh? I'll make this stuff look easy. How about this one? R equals 6 cosine theta. Again, the cosine theta is not in the dictionary per se, nor r by itself. An r squared I could do it, an r cosine theta I could do it, but not an r by itself, not a cosine by itself. So here's a small little tweak that you could try on these. By the way, this is a famous one from back from the last section. This would be a rose petal with just one petal. The maximum would occur when theta is equal to 0. Just so you know, this would be a rose petal with just one petal, or you could also call it a circle. Circle with diameter 6. Just so you know, this is famous too. Hopefully you did your homework and you know that already. Alright, so anyways, back to converting. Here's a nice little trick. You could take this r is equal to 6r cosine theta and multiply both sides by r. That would be legal. So that would give you that r squared is equal to 6 times r cosine theta. And now all of a sudden, look what you've got. You've got a phrase here that's r cosine theta. That's super famous. How much is r cosine theta? X. I told you. And you have something else here. An r squared. Is there a famous way to exchange an r squared for x's and y's? Yes, there's a famous way. R squared can be exchanged for x squared plus y squared. That does it. This piece right here is x squared plus y squared. That piece over there is 6 times x. And you've done it. You've changed it into Cartesian. We've changed it into Cartesian. By the way, this is famous. This is a circle where you've got a linear term, so you need to, if you wanted to do the shifts and the stretching the way we did it earlier in the course, you would collect the x's together and you would set this equal to 0. You would complete the square by taking half of this and adding it to both sides. Half of this would be negative 3 squared. That would give you 9, and you add that to both sides. So you got minus 6x plus y squared is equal to, let's add a 9 here and add a 9 here. It's legal to add the same number to both sides, but that completes the square on the left side. That gives you that x minus 3, the quantity squared, plus a y squared is equal to 9. You see, whoa, there you go. That's a circle. That's a circle. That's got a shift to the right 3. So you could graph that. See, the original circle would be here. The original circle would be here. Well, would it be a circle with radius 3, but then that's the circle without the shift, radius 3. But then as soon as you do that, you shift it to the right 3, and now it ends up being a circle to the right 3, where the center is 3, 0, and of course it's got radius 3. So this matches exactly the rose petal discussion from earlier times, when this coefficient is an odd integer. This tells you the number of petals on the rose. Well, it happens to be just one petal, so it's a circle. Exactly consistent with this conversion stuff and completing the square. Very nice creative idea here to slap an R on both sides so that you can make use of the dictionary here from polar to Cartesian. How about that one? That one looks a little strange. Again, theta is equal to 2.5. If this is an angle, I assume it's radians. Otherwise, it's got no units, so the default units are radians. Otherwise, you'd have degrees to be degrees. Anyways, how do you convert this? Again, you look at your dictionary and you say, hey, there's no theta all by itself anywhere here. I can't really exchange a theta. However, I could exchange a tangent theta. So then we could play this game. You say, hey, if theta is equal to 2.5, okay, if theta is equal to 2.5, then that would mean that tangent theta would be equal to tangent of 2.5. Yes or no? Stop me if I'm lying. Stop me if I'm lying. And this has an added advantage because I can exchange a tangent theta. A tangent theta can be exchanged for what? For y over x. So therefore this guy becomes y over x is equal to tangent of 2.5 radians. Or said differently, y is equal to a tangent of 2.5 times x, which is just some number. Tangent of 2.5, I could even estimate that for us. Tangent, I gotta change this to radians. Make sure your calculator's in radians. Let me see. How do you change it? You go shift degrees to radians. Perfect. Then you would go like this. Tangent of 2.5, we'll first clear everything. Tangent 2.5 is equal to negative 0.75. Aha, so y is approximately negative 0.75x. There you go. It's an equation. It's a line with slope negative 3/4, roughly speaking. Nice, huh? It's converting stuff. At the heart of it, really, is just using the dictionary carefully to exchange things. And when the exchange rate is not apparent, sometimes you may have to tweak the equations just a little bit so you can make the right exchange. Okay? Boy, this is the shortest lecture I've done in a long time. I've got nothing else for you in this section. I'm out. See you guys here next time. Take it easy. Do the homework now. Slowly enjoy it. See you guys here next time. Peace.